So the last talk for today's session is going to be Ilya, Eremin, and so he's going to talk about theoretical aspect of this problem. It's all yours.
Yes. Okay, let me move to the, just remove this one. Okay. Yeah, thank you very much. So now we are sort of back to the theory, and they come from the ambiguity in the Christoph Grote ambiguity in the theory description of the system. And so I'm going to talk about basically correlation effects, discussing the infinite layer and what the new physics you see in the bilayer under high pressure, and try to also to speculate what will happen to the upon phase increase of the layers. Now this is work which has been published, various part of it, and the most recent is just put on the archive. Let me also acknowledge my collaborators. So the work, so for some reason, okay, so the work that I'm going to present on the bilayer nickelates has been done with my collaborators in Bochum. So they are all also in the audience. So Frank Lechermann, my senior colleague here, and also graduate student Steffen Bürzel and Yannick Gondolf. And the work on the infinite layer has been pushed forward together with Andreas Kreisel, and Brian Anderson from the Niels Bohr Institute, and Astrid Römer, and also Piyush was my postdoc who recently moved to the faculty position, and who all contributed to this work. Okay, so now I would like to come back to the issue that Mike was continuously mentioning yesterday, that our initial understanding of the infinite layers nickelates as being kind of a close cousin of the infinite layer cuprates is challenged, and in fact, you probably need a multi-orbital description of the system, and I will present a view where you actually do take into account the correlation, and you see a model which where the dz square orbital from the nickel also play an important role. And then I will try to continue for the bilayer nickelate, but I will assume the conventional structure of the bilayer and discuss what you would expect for the magnetic spin response in this case, and what would be the potential signatures to look for potential superconducting instabilities. Okay, so let me now start showing a slide which is similar to the one which Mike has shown. And in fact, if you compare the DFT results, plain DFT between infinite layer nickelates and infinite layer cuprates, you sort of see that indeed that looks like there is a main player of the 3D x square minus y square orbital, but there is some sign which are coming from the 5D, also hybridizing with the 3D states. And that was more or less the starting point for discussion that you had in the literature, where people were initially proposing that all that becomes irrelevant. So this multi-orbital effect become irrelevant once you move to the to basically once you include the correlation, and then essentially the 3D x square minus y square becomes the most important. Or there is another point of view where the multi-orbital physics is important. And let's of course, you want to ask how the band structure changes once you include the electronic correlation, and unfortunately, the answer to that is not identical, because you can take, so probably is one of the, let's say, advanced techniques that is used as DMFT, but it actually turns out that DMFT also gives a relatively different answer to this question. So one of this is a representative structures that comes from the DMFT plus DGA calculation, which was put forward by Carsten Helte and collaborators. And so his statement, and in his case, he's using a U of the intermediate value of the order of 4.5 electron volt. So what you clearly see is that once you include the correlation at this level, what you see that the main player is becoming indeed a 3D x square minus y square. So this 5D bands basically is pushed away from the Fermi level, and in the entire doping range where you see the superconductivity, they claim that the main player still remains a 3D x square minus y square band, and essentially all the physics that you see in infinite layers, they propose as a kind of a renaissance of the cuprate 3D9 copper oxide physics. Now, at the same time, if you take another example of the DMFT, which is including a much larger value of the interaction, which is still far from the atomic, but of the order of 2 a factor of 2 larger than what Carsten Held is using. And on top of it, what is important, you also include a self-interaction correction on the oxygen. It actually turns out that a completely different picture arises. So namely, what is actually happening is that you have a selective mode transition at nominal concentration, where the x square minus y square orbital is split into the upper and the lower Hubbard band, and the only itinerancy with a weak insulating behavior is basically provided by the nickel 3D z square orbital, which is also has a very flat region near the Fermi level. And that is basically continuous all the way once you introduce the doping. So, and then again, because of the modness of the x square minus y square orbital, the doped hole is not sitting on the x square minus y square, but essentially moves all the way through the 3D z square, which is also very different from the cuprates because of the charge transfer gap between the copper and the oxygen state, that the hole prefers to go to the dz square orbital. And that all continues up to the order of also 30%. And at the 30%, the picture is kind of consistent between both approaches, where you see that all the entire T2G manifold starts to approaching the Fermi level, and that altogether yields destruction of superconductivity because you get some Hund physics, and that is destroying superconductivity. Now, if you now would like to elaborate a little bit on these approaches, which actually Frank Lecherman put forward, you can get a pretty decent agreement with basically with the spin excitation spectrum that is measured by RIX. In this case, however, you cannot describe it in terms of the overdone spin waves coming from the copper 3D x square minus y square orbital. So you are not in the position to describe it with a kind of single super exchange interaction like you do, for example, in the situation when this would be described by the super exchange model. But you still see that the paramagnon that you get still decently well describes the experimental data. And however, this paramagnon cannot be viewed as a single orbital contribution, but essentially come from the orbital manifold, essentially stemming from both 3D z square and 3D x square minus y square orbital. Now, you can continue with the superconductivity with that by basically taking this DMFT-based results, which you parameterize with some slave boson type approximation, and look what kind of superconducting instabilities do you expect. And in this case, since the exact level of incoherency of the x square minus y square is not known, you can model it by simply assuming a different residue of the quasi-particle weight for the d square minus y square orbital, which is here in the middle, and the z square, which is appearing here. And it turns out that the superconducting instability is changing from the 3D, the d wave 3D x square minus the d x square minus y square superconducting gap, which, however, is not a conventional as it acquires a lot of high harmonics, towards an S plus minus, where the gap prefers to change sign between the d square, the d orbitals, and the x square minus y square orbital and the dz square orbital. But you still also have an accidental nodes. And once one of the orbital becomes extremely incoherent due to the residual Hund coupling, you get triplet pairing gap. Now, if you follow the experimental discussion on the superfluid density, what the consequences it has. So the first of the consequences that both the D-wave solution and extended S-wave solutions that you get in the case where the d x square minus y square orbital gets very incoherent, so the S plus minus solution can reasonably well explain the nodal behaviors that you see in the penetration depths. And furthermore, if you look at the STM data, which see a two-gap feature, which see a V-shape and the U-shape type of the spectrum, in fact, you can understand that with a single gap, with either being a D wave, but you have a lot of higher harmonics, because if you look here, what you see is that the D wave structure of the gaps that you get in this region acquires a lot of higher harmonics, which essentially means that it cannot be described by a simple cosine kx minus cosine ky gap. So it means that you have not only a V shape, but also U shape, especially if your Wannier function, if your tip, STM tip comes to a Wannier function where you essentially probes the dz square orbital. So that is also something that in principle consistent with experiment. And I think we, in order to make the proper assignment, you really need to do an ARPIS experiment or angle result experiment to probe the exact symmetry of the superconducting gap. But the most important part of this picture, where this multi-orbital picture, understanding of the phase diagram in infinite layer, is that here you start from a mod behavior of the dx square minus y square orbital, and there is a weak itinerancy coming from the dz orbital, and then it becomes superconducting once one of the dz square orbitals become occupied, such that you also have a flat region near the Fermi level, and that flat region dominates the superconducting region. And once you reach a 25%, where the entire T2G manifold starts also to come from below, and that actually drives again the transition. But what is important that in all this region, the dx square minus y square orbital becomes strongly, remains strongly incoherent. Okay, so now let me move on to the bilayer aniquilates and try to look what we expect there. Okay, again, let's start from the plane DFT, and that is our result that you see, and they actually consistent with, at least visually consistent with what other groups also obtained. So you see a strong hybridization of the z square and the x square minus y square orbital. However, you still can see that the structure of the bands of these two is roughly of the x square minus y square orbital. And you see it's like, you can see it like a bilayer cuprates, but with a strong bonding anti-bonding splitting. Plus, on top of it is our old guest, and namely the 3z square orbital, which is touching the Fermi level near the M point. And what is important is that independent whether it's exactly at the Fermi level or slightly below, slightly above, is that it's extremely flat. So you can see this by, let's say, plotting the three-dimensional version of the Fermi surface and plotting the anisotropy of the Fermi velocity. So you see that, for example, on the near the M point where your z square orbital is located, you have a much more localized behavior. So the value of the 1 over V Fermi is actually as a factor of 2 larger than on the on this bonding anti-bonding x square minus y square type bands that you see here. Another important part is that here you have a 3D8 configuration, so there is a strong hybridization with on the oxygen, and so about 0.4 holes go to the oxygen side, which is very different from the infinite layer aniquilates. But I guess that this is also something that most of you already know. Now, in fact, so this is a DFT result, and indeed there has been a very nice projection onto kind of a very simple model where you can describe it by basically reducing everything more or less to the nearest neighbor hoppings. And if you do that, so one of the most important parameters that you get is this hopping along the z direction that you see, which is describing the splitting on the bonding anti-bonding levels that you see. And what is also nice that you can also identify all the bands also with their bonding anti-bonding character, which is easily separable in this case. Now, what is surprising is that already at the level of the DFT, or let's say tight binding projection from the DFT level, there is kind of inconsistency among the community from the theory side. What is the exact symmetry of the superconducting gap? So the most popular point of view is that you have a bonding anti-bonding S plus minus superconducting gap, which more or less repeats the bonding anti-bonding structure of your Fermi surfaces. So essentially you have a one sign of the order parameter on all the, let's say, bonding bands, and you have another sign of the order parameter and also nodes on the anti-bonding side of the Fermi surface. Now, another solution that actually comes from exactly the same Fermi surface has been found by us and also by all the other groups, which suddenly found that actually the most stable solution appears to be a dx square minus y square symmetry. And that, of course, something that needs to be understood. So what is the difference, despite the visual similarity of the Fermi surface, where the difference comes from? And so actually it turns out that the easiest way is indeed to look into the spin response, to the spin fluctuation, which in principle all computed with all these approaches in this or the other way and put in the superconducting pairing instability interaction. But now you analyze them with respect to the bilayer structure. Namely, we know from the bilayer cuprates that once you have this separable bands into the bonding and anti-bonding level, you can also nicely separate your even and odd susceptibilities, also in the itinerant language. And you can clearly see that all the contribution to the odd susceptibility come from the scattering between bonding and anti-bonding bands, whereas all the even susceptibilities determined by the transition within the anti-bonding to anti-bonding or bonding to bonding. In other words, in a simple language, this you can view as mostly intralayer susceptibility, whereas odd one is interlayer susceptibility. And now what you can do, you can actually analyze what comes out for the even and the odd susceptibility, and you simply compare these two models. So we first let's take the model that Lu et al., which gets an S plus minus anti-bonding superconducting gap. Let's take this model and look what's actually happening. So the first thing you immediately see is that the odd and the even susceptibility have a completely different structure. And that is, you can trace back to exactly the scattering processes that you have between bonding, anti-bonding, or bonding and anti-bonding band. What is interesting is that you have this wave vector that's exactly very similar to the one which is also reported in the RICS at the ambient pressure. So the structure is clear, but what I would like to point out is that if you take the model, which is based just on the nearest tight binding, then the largest contribution is two orders, or not two, a factor of two. Susceptibility in the odd channel is larger than the susceptibility in the even channel. And now you immediately understand why does it get an S plus minus gap, because essentially all the pairing interaction is dominated by this. Now, if you do the same, and now you just change the tight binding parameterization. Now, let me mention that, in fact, the differences in the tight binding parameterization comes because you include just higher order hoppings, and the more hoppings you include in the layer, essentially more and more gain in your even susceptibility appears. And so it turns out that in this case, although the structure of the peaks is actually the same, and that is easily traced back to the fermiology of the system, you see that they are now becoming of exactly the same magnitude. So the peaks are of the same magnitudes, and then it basically means that you have a situation where S plus minus start to compete also with, which is interlayer S plus minus, start to compete with intralayer interactions. And usually we know that D-wave is much more robust against inclusion of the local Coulomb, and that's why D-wave, in the case of susceptibility between the layers and within the layer of the same order, D-wave start to dominate. But another important part is that, again, you see this nice structure, which is very much tempting to identify to be the reason also of the magnetic ordering. And let me also mention that I don't have plots here in the talk, but you can do the same calculation also in the parent at phase, or let's say at the ambient pressure, and actually you see exactly the same structure of the susceptibility, where that one is still the one which is determining the magnetic instability. Now, so now if you start to think, okay, what could be then in this, let's say, assuming that 3 to 7 is the actual structure and the superconducting gap is either one or the other, so you start to think where to to look for signatures. And then generally, given the fact of the strong difference in the bonding anti-bonding character, the immediate thing you start to look for is some charge or spin response, which is again can be separated into the odd and the even part, and then look into the corresponding coherence factors that you expect for the superconducting gap. And one of them, the most celebrated one, we know that this is spin resonance that requires a change of the sign of the superconducting order parameter, and that has been done, including also the speakers and the organizers of this conference. What is also known that in IPCO or in bilayer cuprates, there is also both even and odd susceptibility show resonance behavior, and you can also, there has been nicely traced as a function of doping, and you all can understand it basically by assuming that there is a D-wave symmetry on a bilayer, but simply you have a bonding anti-bonding band slightly splitted in a bilayer cuprates. Now, you can apply exactly the same ideas now to the bilayer nickelates. And we first look at the S plus minus gap, and for obvious reason, because here the gap is changing sign only between bonding and anti-bonding bands, essentially you only see a resonance enhancement in the spin response function only in the odd channel, whereas in the even channel, you see nothing. Now, it's interesting that, of course, it's understandable that to do neutron scattering under pressure is kind of challenging, but you also have an NMR. And let me remind you that in NMR, you see an opposite coherence factor. And if you are able to select also bilayer contribution separated into even and odd part, you should see actually the opposite behavior. So you should see a Hebels-Lichter peak appearing in the even channel and no Hebels-Lichter peak in the odd channel, which again would signify to you that the structure of the superconducting gap is this S plus minus gap. Now, if it is a D wave, then you do have a difference because the band structure is different, but this bonding, anti-bonding, and bonding to bonding transition, they are still different, but nonetheless, they both will show you a resonance enhancement. So that would be more effects, let's say, which are comparable to the bilayer cuprates, except that in this case, you should look at the different ordering at the different momenta to see the resonance enhancement because they are initially different. But the story is kind of similar to the cuprates. So that is what you see at the level of DFT. Now, of course, again, a question, what does happen once you include the correlation? And again, you know, the field is very new, so there are only some indications. So from our results, what we see is that once you perform the same calculation, what you see is also, again, a strong sign of the incoherency and a non-Fermi liquid behavior. So you see that once you do this self-interaction correction DMFT, you see that all the bands get kind of flat. So you get flat region near the Fermi level. And if you try to plot the Fermi surface, you barely see it because everything is strongly incoherent. You have a very large renormalization of the effective mass. And essentially, that means that you have to basically consider more, let's say, pairing in a non-Fermi liquid case. That would be a complete change of the, let's say, DFT perspectives that I presented so far. But there is also another one that has available on the archive, and this is cluster DMFT, where they see a rather a renormalization of the band structure, where again, what they see is that the pocket near the endpoint get shifted below the Fermi level, and that seemed to be also consistent with an ARPIS experiment at ambient pressure. But you still see this renormalized bonding, anti-bonding bands, and you would, of course, still see this ordering wave vector, which I just indicated, which also would be in favor of the S plus minus state. But this is direction along which the theory at the moment is developing. Okay, I think I'm now at the end of my talk. So what I tried to convince you that independent, let's say, on the final issue, let's say, on the crystal structure of the bilayer, I think the general understanding is that you certainly need a multi-orbital physics to describe superconductivity, normal state, and the overall spin dynamics in this system. And you have a competition between D wave and S plus minus superconducting order parameters. And to be honest, I'm more in favor of a B1G, especially because for large Fermi surfaces, there is always this problem of the large Coulomb repulsion that you have, yes, and understanding of this orbital or layer dependent susceptibilities, so basically which you can, of course, generalize for the trilayer and also for the heterostructures of the trilayer monolayer, which is an interesting task, becomes crucial to understand the physics of the system. Okay, thank you very much.
Thank you, Ilya. Yeah, so we'll get the one by one. Mike.
Yeah, Ilya, nice talk. And I think it's related to what Ming was saying last night. They saw this flat mode in neutrons. You could think that, well, you're going from anti-aligned planes to aligned planes. That's what they're seeing. The problem, if you look at the RICS data, the new paper that just came out, they have polarized RICS, and you look at this data, there's basically, as far as I can see, no L dependence to the data.
Well, what I understood is, somehow I understood that their peak is somehow consistent with being in the odd channel if you look at the value of L. But what you are right is that the intensity immediately goes away once you leave this point. So somehow I interpreted it that in principle you can understand these peaks as being in the odd channel. But again, this is something that we maybe can discuss.
Yep. Okay. Yeah, I mean, I see the data. It doesn't look like there's much change, unlike, say what Tronquata saw in YBCO back in the day, but we'll see. Yeah.
Okay.
Carol?
Very quickly on the point regarding nearby even or odd symmetry, would you estimate you're close to that transition, meaning as a function of pressure, tuning, C-axis coupling or something, could you cross that experimentally? And if I could sneak in a second related to that naively, would you expect the, let's say the plasma, or the Josephson plasmon response to be different between the two situations? Thank you.
You are talking about infinite layer, right?
No. So the bilayer case.
Oh yeah, absolutely. So that's actually, you do expect to see a very similar. So if you look at the charge response, it has exactly the same structures, where there's even an odd type of separation, except that you just need to take into account the long-range Coulomb repulsion. But the structure of susceptibility in that case is exactly the same. So just, of course, there is a different denominator, but overall structure of the charge susceptibility looks very similar. So I would expect a very different behavior of the plasmon in the D wave and the S plus minus case. Along the same line. You have to be a bit careful because typically in charge channels, the coherence factor is opposite to the spin channel. So that would mean that there you would expect something interesting for the S plus minus gap. You would expect something interesting in the even channel to happen, some enhancement, and not in the odd channel, because there's the coherence factor is just opposite.
Yes.
I just wonder if that's, I'm sure it's hard, but possible experimentally in a diamond anvil cell to do.
No, it's not possible.
No,
not by neutron standard. Yeah. No, I mean, yeah. I mean,
Okay.
the volume fraction is too small. I mean, it's not possible.
Yeah.
So theorists can speculate any way they want.
Well, but okay. So my let's say so this structure you should be able also to see, of course, at ambient pressure. So it's surprising that you change the crystal structure. Of course, there is additional folding, but all the peaks are actually still there. Once you.
Yeah. So Ilya, very nice talk. I just want to follow up on this DZ square because we found that whether it's A1G or B1G really depends on whether DZ square is crossing the Fermi energy or not. And now I've only seen one APES experiment having the data publicly available, and seems like DZ square is not crossing Fermi energy. I was wondering what your thoughts are about that, whether it's robust or whether it's Yeah.
So you are talking also about bilayer, right? At the ambient
Yes,
pressure.
that's correct. Yeah.
Yeah, that's true. Well, that's so you can immediately see which peaks will not be there in the, again, starting from the itinerant picture. I would tell you.
I think Ilya, I got the picture from your theory calculation, but I was just wondering, just in general, maybe it's more for experimentalists, maybe just see whether you have thought whether that's an intrinsic feature that the dz square is not crossing the Fermi energy. Or
Well, it is not the case. Let's say again, there are some DMFT calculation which do see that there is a shift of the Fermi level. There was also one paper on the archive today which also argued in this favor. There is also experimental data. So let me put it in the following. So if you are beyond the Fermi liquid and work in the, let's say, in a strongly incoherent regime, it doesn't really matter whether z-square orbital is crossing the Fermi level or not, as you know.
I agree with you on that.
In that case, you know, there will be still signals, there will be still an important physics. So even if it is below the Fermi level, it's still flat and it's very, I mean, it's within 50 millieV is the Fermi level. So the physics will be still there.
Good. I mean, I agree. So experimentally would be good for experimental APES colleagues to help us sort that out. Right.
Yeah. Okay. Any other question? Matthias?
Yes, I have a question about the spin resonance mode. So you propose this distinction, the odd and even channels, to learn something about the gap symmetry. But so if I think, so it looks to me that also the energy of the resonance mode is different for you to do two cases. But if I remember correctly, there's this simple scaling relation between the energy of the spin resonance mode and TC.
Mm-hmm.
Yes, in a single band. Okay, so there is a kind of phenomenological knowledge that the ratio of the resonance peak over K-Boltzmann TC is of the order of 5.2. Now, again, here, I would say it's roughly fulfilled because, so here you have, I mean, assuming that you have a gap of the order of 15 millieV, and so that means that would be a position of the 30 millieV would be a position of the 2 delta. And essentially by looking at the position of the resonance peak, I would say it's roughly of the right order. Again, here, let me mention, we use the same value of the interaction. So the exact value of the interaction is not known. So in this case, you can also make it a bit sharper in the other model as well. So I would say that at this point, we are not at the level of the, let's say, complete microscopic theory, more at the level of the qualitative prediction. And I would say this is what I can at the moment contribute. I even would not take this number very seriously. So it's just the position of the Q vectors is maybe some things that you can take seriously from this calculations.
I see. Thanks.
Yes, thank you.